And 11th chapter is going to be chi-square distribution. All these methods that we are going through are useful in different situations. And one of the situations is such that we cannot use normal distribution or t-distribution or any of the earlier distributions. So this is a new distribution that you come across, and this will be useful if you are comparing more than two things. In binomial, like we had two outcomes. Here you can think of multinomial, so more than two categories. And chi-square distribution, as the name indicates, is a skewed distribution. If you make a picture of chi-square distribution, it will be right-skewed. It will always start at 0. It cannot be negative because it is square. So typically we use this symbol for chi-square. So we'll go through some examples of application of chi-square distribution. Mainly in this chapter we cover two applications. One is test of goodness of fit, and second one is test of independence. Let's say you want to study student preferences at UMass Dartmouth, like what fast food chains they like. We may have a set of null and alternate hypotheses. So there is no preference for fast food chains. So that's the null hypothesis. It assumes that everything is equal. There's no particular pattern here. And alternate is opposite of this. So there is preference for fast food chains among students. Obviously, to test this hypothesis, we collect data. And suppose you collect data and this is what you get. So suppose for McDonald's we have in the sample 120 students, KFC 80, Domino's 100, Subway 70. Whenever you collect data, obviously there will be some variability in the data. All the numbers will never be exactly same. So we have like 70, sometimes 80, 100, 120. You repeat this study again, the numbers may change. So maybe this becomes 75, this becomes 90 or whatever. So the question basically we are trying to answer is whether whatever differences we see are real or they are just sampling fluctuation. You take another sample, these numbers will change. For that we use chi-square test. So assumption is that if we go by null hypothesis, all these numbers should have been equal. So if you calculate probability, you should have got 25% of the students for the first one, 25% second, 25% third, 25% fourth. So they should have been equal, but clearly they are not equal, but we want to test whether what we see is real or not. So I'm going to create a new file, and again I'm going to save this as chapter 11. So that it gets listed here. So this is chapter 11. I'm going to put this data that we have in data by pointing an arrow towards data and then providing it with C and parenthesis all those numbers. So 120, 80, 100, and 70. So once I run this, so this data that we stored shows up in third window. And this data has some names, so I'm going to use names. So as you type names, this names comes up. So I'm selecting that, and then names for what? Names for these data. So I'll point an arrow and give the names with quotation marks. So first one is McDonald, and then you have KFC, comma, Domino, within quotes, and last one is Subway. So just providing the names. And if you simply type the data, that's where our data is stored, and run, this is what you get. This is what we had. For each fast food chain, we have related numbers. The probability that I mentioned, P, should be 0.25 for each, because that's what we are assuming in null hypothesis, that they are all same, so 25%. So with that, we should be ready with chi-square, chisq. As you type that, chisq.test will pop up, select, and then say my data is in data, and P equals probabilities are in P. So P equals P, and then run. Most important thing is the P value, which is 0.001. It also calculates or reports degrees of freedom. So for chi-square, when you have 4 categories, 4 fast food chains, so 4 minus 1 is 3. So how this degrees of freedom is calculated? Simply number of categories minus 1. So 4 categories, 4 minus 1. If you had 10 categories, 10 minus 1. So very simple. We do this chi-square test and get a p-value of 0.001. And if you are considering 95% confidence interval, so your alpha is 0.05. So since p-value is less than or equal to alpha, we can reject the null hypothesis HO and conclude with 95% confidence that fast food chain preferences differ among students. Sports participation versus school year could be another application where chi-square distribution can be used, where null hypothesis is sports participation is evenly distributed across school years versus and you collect data and get for different levels count of students. So freshman, sophomore, junior, and senior years, you get 50 students here, 70, 60, and 40. So again, if you are collecting sample, these numbers will vary up or down. You collect another sample, you may get slightly different outcome. But the key question is whether there is a uniformity in these numbers or not. So this was number 1, and this is number 2. Sports participation versus school year. This is similar setup, so I will use data and store 50, 70, 60, and 40. So names for our data. So again, within quotes, first one is freshman, sophomore, junior, and senior. So that if you type data and run, whatever data we had shows up. Our probabilities are 0.25 again. So for each category, we'll say 0.25, 0.25, 0.25, 0.25. Now this is purely coming because of our null hypothesis. We are assuming that they are all same. We can do chi-square now. Chi-square, our data is data and probabilities are in P. So P equals P. And in no time, it does the chi-square test for you. So this is called goodness of fit test. And once again, this value is small, 0.02. Or if you round this to 3, so 0.03. So we got P value 0.03. And we are assuming alpha of 5%. So out of these two, we are rejecting this in favor of HA. So sports participation is not evenly distributed across school years. So, and conclude with 95% confidence. So sports participation is not evenly. So these two were examples of goodness of fit test. And I'm writing complete conclusion so that you are also aware that when you are submitting your homework assignment, you write it fully. So just saying that we reject or we accept, that's not enough. So another example. So this time, I will switch to second type of application of chi-square. So first one was goodness of fit. Second one is test of independence. So for this, I will use an example of, so somebody may be conducting a study to compare and see whether gaming console preferences versus gender, they are independent of each other or not. Let's say the null hypothesis is so gender is independent of gaming console preferences versus gender is not independent of gaming console preferences. Because those can have like implications in so many ways for gaming companies. Gender could be male or female. Gaming consoles, let's say PlayStation, Xbox, Nintendo. So after you collect data, you find 50, 40, 30 for male, and then 30, 20, 50 for female. Just by looking at this data, it may be difficult to say anything clearly. So this one is going to be test of independence. And this example is gaming console versus gender. So in this class, we have been using R programming, and this is a technology nowadays almost needed in every field. Whether you become an accounting major or finance major, operations management, MIS, marketing. So this is going to be a very, very handy tool. And most of the employers now expect some skills in these kind of technologies. And having this actually by the time you reach your senior year, so if you strengthen these skills, your value increases almost by like $15,000. So if your starting salary is, let's say, without this about 70K per annum, it can add almost like minimum 15K very easily, because not many people have this skill. So those of you who are able to at least do some basic things will definitely elevate yourself to a much higher level. So let me put this in R. The only thing is, because now we have this table, so it has to be done slightly differently than what we did earlier. This is called contingency table, two-way table. I'm going to put this again in data by pointing an arrow towards data. So there are two rows, and in R you can enter those rows and bind them together using a function called row bind, but you simply type R bind, which stands for combining rows. So I'm going to select that and then enter with C first row of data, which was 50, 40, and 30, and then put a comma and again another row of data using C, second row, 30, 20, and 50. So that we can run. So because now we have like 2 dimensions, so I will use DIMNAMES, dimension names for our data. So we point an arrow this time again, this time because we don't have just one row, but we have a list. So I will use list. So first one we call gender is equal to C and parenthesis within quotes male, comma, within quotes female. And then I go to the next line and say console. First one within quotes PlayStation. Second one is Xbox. Third one is Nintendo. Once I run this and type data and run, so you can see your data is exactly in the same format that we wrote down. So once you have this chisq.test data, run, and you should be done. So chi-square-test gives you p-value of 0.0005. So one thing different here is, last time there were 4 categories and we said degrees of freedom is 4 minus 1. Now you have 2 by 3 matrix. So degrees of freedom in this case is going to be, I can write down so that you remember it. Degrees of freedom equals number of rows minus 1 times number of columns minus 1. So number of rows 2. So 2 minus 1 is 1. Number of columns 1, 2, 3. So 3 minus 1 is 2. So 1 times 2 is 2. So that's why you see degree of freedom 2. Since p-value is less than or equal to alpha, we can reject HO and conclude. So we are rejecting this, we are accepting this. So we conclude gender is not independent of gaming console preferences. So there's a clear preference, different preference among male versus female. Okay, last example. Social media platform preference versus age group among younger and older teens. So what we are trying to do here is we are capturing in the form of null and alternate. So age group has no effect. Age group has no effect on preference for social media platforms, whereas HA is age group affects the preference for social media platforms. So again, to prove or disprove anything, we need data, and suppose this is our data. So we collect data on different age groups, 14, 15, 16, 17, and 18. Social media platforms, Instagram, Snapchat, and TikTok. And suppose your data looks like this. What degrees of freedom will you get with this data set where you have two variables, social media platform, age groups, and each variable has three different levels. So what should be your degrees of freedom here? If you are using chi-square-test? 4. So 3 rows, 3 minus 1 is 2. 3 columns, 3 minus 1 is 2. 2 times 2 is 4. So 3 minus 1 times 3 minus 1 equals 2 times 2 equals 4. Social media. So this example. And to save time, I'm going to copy and paste what we did earlier. I need to change data. So first row is 40, 30, 50. Second row is 50, 40, 60. And I need one more row, so I will add C and 30, 20, 40. So that will be data. Instead of gender, I have group now, age group, and 14, 15, 16, 17. I add the third one, 18. Instead of console, we have platform, social media platform, Instagram, Snapchat, and TikTok. So we run this, and if you look at the data, it should match with the data you had. Looks exactly same. 50, 40, 60, 30, 20, 40. So that means we can run chi-square-test. So p-value we get is 0.95. So p-value based on chi-square, your p-value is 0.95, whereas alpha is only 0.05. So conclusion, since p-value is less than equal to alpha 0.05 we are checking that and we find it is not the case, we cannot reject null hypothesis and conclude with 95% confidence. So we cannot reject means this is true and there's no proof that there's any difference between the two. So basically it is saying these two variables are independent. So in these three age groups, there's no preference for any particular social media platform. So age group has no effect on preference for social media platform. So when we are concluding that age group has no impact, obviously it is in the context of whatever age groups we have chosen. So we cannot generalize this to any age group. So if like somebody wants to make it more clear, you can say ages 14 to 18. Okay, so I think as far as chapter 11 is concerned, we are done with that now. The only chapter that remains for this course is simple linear regression that will start in the next class.